What is frequency? Frequency is defined as the number of oscillation that takes place in 1 second. We are studying about the characteristics of simple harmonic motion, where the acceleration of a particle is directly proportional to displacement and the acceleration of the particle is always directed towards the mean position. When two vibrating particles are undergoing oscillation, if you measure the difference between their phases, so it will give us the phase difference of two vibrating particles. Hello everyone, welcome to session 1 of chapter 14, Oscillations, one of the important chapters and the chapter with more weightage examination point of view, Oscillations. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. In this chapter, Oscillations, we are going to understand what is the basic definition of oscillations, what is the primary terms which involved with oscillation concept, and also the concept of simple harmonic motion. How does the time period of object depends on the length and the mass? How does this time period related with the length and mass of an object by taking the simple pendulum and the spring as an examples? What is amplitude? What is displacement? What are the different types of oscillations? And many more. It's one of the important chapters as well as the interesting concept. Let us now go through with the introduction part. So in introduction, we are going to tell you what is oscillation. So oscillation is nothing but an object which is undergoing a motion, and the motion is to and fro. It is nothing but a to and fro motion of an object. So what is a periodic motion then? What is oscillatory motion? What is periodic motion? Are they same, or what are the differences between them? So the periodic motion is nothing but a motion that repeat itself after a regular interval of time. The motion that repeat by itself after a regular interval of time, or we can say that the motion in which a particle repeats the same path again and again at regular interval of time is called as periodic motion, and hence the name periodic. It takes place after regular interval of time, it repeats itself, or it follows the same path after regular interval. For example, the best example to understand this is the revolution of planets around the sun. They undergo motion around the same path. So after regular interval of time, it continues its motion around sun. So that is the best example to understand periodic motion. And we have few more examples for this, that is oscillation of mass suspended to a string. If you attach some mass and it is allowed, the spring is allowed to execute oscillation, after regular interval of time it will just be in motion, and it is also called as a periodic motion. And oscillation of bob of a simple pendulum, though it is oscillatory motion, we can also give an example for periodic as well, since they takes place at regular interval of time. And oscillation of air particles during the propagation of sound waves is also a periodic motion. So now we can say that after knowing about oscillatory motion, we can conclude that all oscillatory motions are periodic, but all periodic motions are not oscillatory. Then what is oscillatory motion? It is nothing but the to and fro motion of a particle about its mean position. This is the important criteria we need to remember, that is about its mean position. If a particle is undergoing to and fro motion, then it is oscillatory. Now consider an example for revolution of planets around the sun. Though the planets will revolve around the sun and reaches its mean point or its own position after regular interval of time, it is not like a to and fro motion like this. It is not a to and fro motion. It's like complete revolution, which means the motion of an object around the sun at regular interval of time, and hence it is an example for periodic motion. But consider an example of simple pendulum. If the pendulum is disturbed, the displacement is there, then according to simple harmonic motion, after reaching the extreme position, the pendulum bob will come back to its mean position, and it will go back to its another extreme point, and again it comes back. So this is oscillatory motion. So from this we can say that all oscillatory motions are periodic. So now the example for oscillatory motion is again mass suspended to a spring, vibrations of wire of musical instrument, as well as the vibrations of tuning fork. All these are an example for oscillatory motion. So now this is about the basic thing which we need to understand about oscillations. What is periodic? What is oscillatory? Next, we have some important terms that are related with oscillatory motion. So let us begin with period. Period is nothing but the time period, and it is denoted by capital T. So time period is defined as the time in which a particle completes one oscillation. What is the time required to complete one oscillation for an object is called as time period, or it can also be defined as the smallest interval of time after which the object repeat its motion again and again. It is called as time period. What is the SI unit of time period? The unit of time period is second, and it is denoted by a symbol called yes. So next we have the displacement, very important term which we use frequently in this chapter, displacement. So what is displacement? We all know how to define displacement. That is nothing but the distance traveled by an oscillating particle. Because we are talking about a particle which is undergoing oscillations here, we don't use the term object. It is nothing but the distance traveled by an oscillating particle at any instant from its equilibrium position. Equilibrium position is nothing but its mean position. You can see here in this diagram, A is its equilibrium position and B and C are its extreme points, which means this is a mean position. After it gets accelerated, it will get displaced to the extreme position. So what is the distance that is moved by an oscillating particle from its mean position is called as displacement of a particle. So next is the frequency. What is frequency? Frequency is defined as the number of oscillation that takes place in 1 second. So how to define frequency, or how to write the expression for frequency, how to find the frequency of an oscillating particle with the help of this formula. Number of oscillations of particle divided by what is the time taken to complete that number of oscillations. So we will get the frequency of oscillation of a particle. The SI unit of frequency is Hertz, and it is symbolically represented by Hz. Since it is named after a scientist, H should be with capital letter. Now what is the relation between the frequency and time period? So in the previous slide we have studied about the time period, that is time required to complete one oscillation. Frequency is number of oscillations that takes place in 1 second. How they are related with each other? The relation between T and F is T equals 1 by F, which means the time period and frequency are inversely proportional to each other. Next we have amplitude. Amplitude means the maximum displacement of an oscillating particle from its mean position. Say for example, if this is the mean position, whatever the acceleration is given to this object which is undergoing oscillation, according to that the particle will get displaced. The maximum displacement. So here in this example, this is the maximum displacement. So the amplitude is this much. Say for example, if it is displaced more, what is the maximum displacement that we can measure, which give us an idea about the amplitude. So mean position, as I told before, it is nothing but the equilibrium position of an object without changing its position or without undergoing any displacement, which means when the particle is said to be in its mean position, the displacement in this condition is 0. Another important term that involved in this concept is phase. It is denoted by a Greek letter phi. So what is phi or what is phase? As we know, displacement gives us what is the maximum distance traveled by an oscillating particle. Amplitude is nothing but the maximum displacement of the particle. Time period gives us what exactly the time is required to complete one oscillation. Frequency is number of oscillations that takes place in 1 second. Then what is this phase? Phase gives us an idea of the position, or it is defined as the state of vibration. What is the state of vibration of an oscillating particle? That can be understood with the help of phase. Here phase is nothing but again it tells us the position and orientation of a particle which is undergoing an oscillation. The SI unit is radian, or it can also be defined as the phase of vibrating particle at any instant is a physical quantity with which completely it expresses the position and direction of motion of particle. As I said, it gives us the position and orientation of and the state of vibration of a particle is called as phase. So all these position, the state of vibration or the orientation are with respect to time, which means what is the position or the state of vibration at that particular instant of time is called as phase. And this phase can be calculated with respect to its mean position. So now we are moving on to an important concept, that is simple harmonic motion. In short, it is SHM, which means simple harmonic motion. So what is simple harmonic motion? To understand the simple harmonic motion, let me give you an example. Let us take simple pendulum as an example. Now it is at mean position. Suppose if we apply some force, what happens? It will get accelerated and it will move to its extreme position. It will move to its extreme position, which means it will get displaced to its extreme position. Here now it is accelerated and the particle is displaced. So how much the particle will get displaced? Whatever the acceleration we apply, so much of acceleration or the force it will get and it will displace accordingly. So simple harmonic motion says that the acceleration of a particle is directly proportional to its displacement. And after displacing, after it reaches its extreme position, this simple pendulum bob, it will not go around anywhere, wherever it wants, but it will come back to its mean position. So simple harmonic motion definition is very simple. The acceleration of a vibrating particle is directly proportional to displacement and it is always directed towards mean position. It says that it is an oscillatory motion in which the acceleration of a particle is directly proportional to displacement, which means how much ever we accelerate it, it will displace from its mean position, and after displacement it will come back to its mean position. So, and it is always directed towards the mean position. I repeat, the acceleration of a particle is directly proportional to displacement and it is always directed towards the mean position is the definition for simple harmonic motion, a very important concept to understand. So let us now study the characteristics of simple harmonic motion, which is very important question exam point of view as well. So it is a periodic motion because we know that an object which is undergoing oscillation will also repeat its motion at regular interval of time and we can say it as periodic. So the first thing is simple harmonic motion is a periodic motion and it is a to and fro motion of particle about its mean position. Consider an example of simple pendulum. Again, it gets accelerated, it will get displaced. Again, it will come back to its mean position, which means it is a to and fro motion of a particle about its mean position. The acceleration of the particle is directly proportional to displacement. We are studying about the characteristics of simple harmonic motion where the acceleration of a particle is directly proportional to displacement and the acceleration of the particle is always directed towards the mean position. See, consider this example again, that after displacement it will come back to its mean position, which means the acceleration is always directed towards the mean position. The frequency and period of oscillation are independent of amplitude. We know what is amplitude, it's nothing but the maximum displacement. So frequency and time period are nowhere related with the maximum displacement, or it is independent of amplitude. And the acceleration of the body is maximum at extreme position and it is zero at mean position, because when it gets accelerated it will reaches to the extreme position where it is maximum, and after coming to its mean position or by coming back to its own position at mean position, the acceleration is zero. But how to accept it? We'll have to substitute certain values in few expressions to accept this point that we'll be doing in further slides. So now we came to know what is simple harmonic motion, what are the characteristics of simple harmonic motion. So simple harmonic motion is of two types. One is a linear simple harmonic motion, the other one is angular simple harmonic motion. The best example to understand the linear simple harmonic motion is nothing but the spring, which is attached with a mass. So what happens if this gets displaced, which means if it is accelerated, it will stretch and there causes an oscillatory motion of the spring, which means the mass will get stretched and it will be disturbed. Again, it will go back to its mean position. It will come to extreme end, mean position, extreme end. So this is the best example to understand linear simple harmonic motion. It is nothing but the motion in which a particle, so the particle moves along a curved path. For example, a simple pendulum. So simple pendulum is an example for a curved path because it will get displaced to the extreme position. Again, it will move in a curved path to other extreme end. So this is the angular simple harmonic motion. So next we will move on to the displacement equation of simple harmonic motion, a very important equation to understand the chapter, displacement equation. So in simple harmonic motion, the displacement displacement is a sinusoidal function of time. The graphical representation also says the displacement is a sine function of time. So the displacement of a particle executing simple harmonic motion is given by the equation y is equal to a sine omega t. Here y is nothing but the displacement, a is the amplitude, and omega is the nothing but the angular velocity, t is the time. So it can also be written as y is equal to a cos omega t according to its orientation, but frequently we use this term a sine omega t. We know what is omega. Omega in terms of frequency also we can write. So it is 2 pi divided by t. Now this equation becomes y is equal to a sine 2 pi divided by t into t. So now let us understand the graphical representation. We have an equation y is equal to a sine omega t, but omega is 2 pi divided by t into t. Let us give different values for t. Say for example, when t is equal to 0. What happens to this equation? Y becomes 0. Correct? Because this gets multiplied. So here we get 0. When time period is 0, we get no displacement and hence it is at its mean point. Next, we'll choose when t is equal to capital T divided by 4. That is 1/4 of the time period. So now the equation becomes y is equal to a sine 2 pi by t into t by 4. T will get cancelled, 2 ones are, 2 twos are, sine pi by 2 is nothing but sine 90, sine 90 value is 1. So we will get y is equal to a. What is a here? A is nothing but the maximum displacement, that is amplitude. So it will reach this point at t divided by 4. Similarly, let us now try with another value when t is equal to capital T. What happens to displacement equation? Y is equal to a sine 2 pi by t into t. T and t will get cancelled. Pi is 180. 180 into 2 is 360. So sine 360 is 0. So then y value will be equal to 0, which means when this is at t, again we will get 0. Next we will try another point, that when t is equal to t by 2. Again we will get y is equal to a sine 2 pi by t into t by 2. 2 will get cancelled, t will get cancelled, and a sine pi we will get. What is sine pi? Sine pi is nothing but sine 180. The value of sine 180 is -1. So we get y is equal to minus a. So minus a means the negative amplitude. Maximum displacement to the negative side. So here this is at t by 2, which means this is how the displacement varies with time, and hence we will consider the simple harmonic motion is a sinusoidal function with respect to time. Now let us write the expression for simple harmonic motion. To write the expression for simple harmonic motion, let us consider a particle P which is executing uniform circular motion. So the particle P is executing uniform circular motion in a circle of radius A as shown in the figure. So it is moving in a circular path, and hence it is having its angular velocity, and it is given by omega. Let the particle starting from here, so rotates in a circular way and it reaches y, x dash, y dash, again it will come back to x. So it starts from x, rotates through an angle theta in time t. You can observe here, it reaches this point and this is angular displacement, it is given by theta. It takes certain time to reach another point to make an angle theta and let it be time t. Now the angular velocity is given by, angular velocity is omega, which is equal to theta divided by t, angular displacement divided by time taken. Or from this we can write theta is equal to multiplying these to omega t. So remember, theta is equal to omega t, where theta is angular displacement which is equal to angular velocity into time. Next, the displacement always represented by a letter y of a projection P on the diameter y dash is given by y is equal to on. See here, the particle reaches at this point P, the projection of this is given by n. So the displacement y dash along this diameter y dash is ON, and it is nothing but Y. Y is nothing but the displacement. So now this will become one triangle. So consider this triangle, and this triangle is OPN. So from this we can define sin theta. So what is sin theta? It is opposite by hypotenuse. So opposite is ON, hypotenuse is OP. So now we can write that sin theta is equal to ON divided by OP. So now what is ON? ON is given by Y. OP is nothing but the radius A. So we have substituted sin theta is equal to Y divided by A, or from this we can write Y equals A sin theta. What is theta? Theta is angular displacement. Here we have derived theta is equal to omega t. So we got the equation Y is equal to A sin omega t. If phi is the phase constant, or phi, as I said, it gives the representation or the position or state of vibration of a particle, the orientation of a particle. So if this is the phase constant or initial phase can also be called as epoch, then Y is equal to A sin omega t plus phi is the displacement equation of simple harmonic motion. So let's move on to the next concept, that is force constant. It is given by a letter K. What is force constant? It is defined as the force required to give a unit displacement of a body. It is given by K is equal to F divided by Y, where F is nothing but the force required, Y is nothing but the displacement. Since it is F by Y, the unit of force is Newton divided by displacement is meter. So the SI unit is given by Newton per meter. That is the unit for force constant. So we have another important term to understand in the study of simple harmonic motion. It is the initial phase or epoch. So what is initial phase? It's a phase of vibrating particle corresponding to time t equals 0. So what is the SI unit of this phase? It is given by radian. So phase difference can also be measured as the difference in the phase angle of two vibrating particles at any instant of time. When two vibrating particles are undergoing oscillation, if you measure the difference between their phases, so it will give us the phase difference of two vibrating particles. But how to find that phase difference? By finding the phase angle between the two vibrating particles at any instant of time. So when these two vibrating particles cross their mean position at the same time, moving in the same direction, say for example we have displacement, that is y1 is equal to a sin omega t, y2 is equal to b sin omega t. Two vibrating particles are moving in the same direction, they cross their mean position at the same time, then the phase difference between them is 0. Imagine just two vibrating particles which are moving and crossing the mean position at the same time, and they are also moving in the same direction, then there is no difference between the phase between them, that is the phase difference between the two vibrating particles is 0. Similarly, when two vibrating particles cross their mean position at the same time, moving in the opposite direction, then there is a phase difference between them, and it is given by y1 is equal to a sin omega t plus pi and y2 is equal to a sin omega t, because in this condition we are considering that a is ahead of particle by half vibration, since they are crossing at the same time, crossing the mean position at the same time but in the opposite direction. The phase difference exists, and it is given by a sin omega t plus pi and y2 is equal to a sin omega t. These are the displacement of two vibrating particles. So next important term is velocity. How to find velocity? It is nothing but the rate of change of displacement of particle. So the rate of change of displacement means, we know what is displacement. It is y is equal to a sin omega t. Rate of change of displacement means dy divided by dt, which is equal to a sin omega t, d by dt of sin omega t. So now if you differentiate this with respect to chain rule, so we will get a omega d by dt of sin omega t is cos omega t. So this is the expression for velocity, a omega cos omega t, or we can also write it as v is equal to omega root of a square minus y square. So what are the special cases? When the displacement is 0, displacement means y. When y is equal to 0, what about the velocity? Where the velocity of a particle is maximum and minimum, we can calculate by this special cases. At equilibrium position, there will be no displacement. For example, consider consider the simple pendulum. This is the mean position or equilibrium position, and here the displacement is 0. When y is equal to 0, substitute here in this equation, v is equal to omega root of a square minus 0, and we get v is equal to omega root of a square. Square and square root will get cancelled. It is omega a. So it is the maximum velocity we can observe at the mean position. So at extreme position means there is a maximum displacement. So we say that y is equal to a. It reaches the maximum displacement. That means it has got some amplitude. So y is equal to a, and this equation becomes v is equal to omega root of a square minus, when y becomes a, again it will be a square, and this will be 0. So v is equal to omega into 0, which means 0. We will get velocity 0 at extreme positions. At mean position the velocity is maximum, at extreme position the velocity is minimum. Similarly, we can write the expression for acceleration. As we all know, the acceleration is nothing but rate of change of velocity, that is dv divided by dt. What is v? We have a omega cos omega t. So if you differentiate this, you will get minus omega square. Y is an expression for acceleration, where a is acceleration of a particle, omega is angular frequency. It can be written as 2 pi f, or it can also be written as 2 pi divided by t, since f and t are inversely proportional, and y is the displacement of particle. Now, where the acceleration of a vibrating particle is maximum and minimum, we can also calculate that as special cases. When y is equal to 0, acceleration becomes, according to this equation, minus omega square into 0, which will be 0 only, which means at mean position the acceleration is minimum, but the velocity was maximum. Now let us say y is equal to a, that is maximum displacement, and this equation becomes a is equal to minus omega square into a, or we can write it as minus omega square a, or it can be written as minus omega square a to differentiate between amplitude and acceleration. So acceleration is maximum at extreme but minimum at mean position. So we have come across the force constant K. Now let us state force law for simple harmonic motion, and we need to derive the equation omega is equal to root of K by m. It's very important. So force law states that the force acting on a particle executing simple harmonic motion is directly proportional to displacement of the particle from its mean position, and it is always directed towards the mean position. According to simple harmonic motion, we know about this, and according to this law, that is y is directly proportional to f, or f is directly proportional to y, which means the force is directly proportional to displacement. Y is displacement. So this proportionality symbol can be equated by introducing a constant, and that is minus k. Why it is minus? Because the particle which is displaced, which will come back to its mean position, that is in opposite direction, and hence f is equal to minus ky, where k is the force constant and y is the displacement of particle from its mean position. Now we have to derive the equation omega is equal to root of k by m. So let's write the expression for acceleration, that is given by a is equal to minus omega square y. But from Newton's second law of motion, that we know that f is equal to m into a, and a is nothing but minus omega square y. I am just substituting the same, so we get f is equal to minus m omega square y, and negative sign indicates that the force is always directed towards the mean position. As I said, displacement and restoring force are opposite to each other, and hence we have to represent this with the negative sign. So now the equation 1 is the force law of simple harmonic motion that we have studied here, that is f is equal to minus ky. So let it be equation 1 and 2 respectively. Now by comparing these equation 1 and 2, we get, here also we have for f the equation minus m omega square y, and here also it is minus ky. Just equating these two, we get k is equal to m omega square. How means it is minus m omega square y, which is equal to minus ky. Minus and minus will get cancelled, y and y will get cancelled, and we remain with k is equal to m omega square. So that is our equation 3. K is equal to m omega square, and from this equation omega square will be equal to k divided by m, but omega is equal to root of k by m is the desired equation. That is what we were supposed to derive, that is omega is equal to root of k by m. So dear students, in today's session, we have come across what is the concept of oscillation and the terms involved in it, and basic definitions of simple harmonic motion. With simple examples, we understood the concept of simple harmonic motion. And in the upcoming sessions, let us learn more about the chapter called oscillations. Until then, keep learning all of you. Thank you.